Okay, what I hope to do with this video is give you a new perspective on space-time, which is a model that I don't find very useful anyways. But I still think it's important to get across this way of looking at space-time. And it involves understanding what time and motion fundamentally are and breaking motion into two kinds of motion, two fundamentally different types of motion. So one type of motion that is probably the most obvious type of motion is inertial motion. So, motion in a straight line in a certain direction in three-dimensional space. And we've known since Galileo and Newton that this is relative and it depends on a frame of reference. So that's one type of motion. Now, we can't use this type of motion to measure time, and the reason we can't is because it's frame dependent. If you change the frame, you change everything. So a better way to measure the passage of time would be to use the second kind of motion, which is frame independent. And the simplest type of the frame independent kind of motion would be rotation. So if an object, so let's say you have a planet like Earth, it's both rotating and moving in a certain direction at a certain speed. It's two types of motion. Now, let's say that you have an observer moving at 0.9 c, or 90% of the speed of light relative to Earth, and the Earth is also moving relative to the observer at 90% of the speed of light. According to special relativity, that observer should see Earth slow down in its rotation because it sees the Earth moving rapidly relative to them. And the speed of rotation should reduce by down to about 43% of normal. So that's time dilation. This doesn't have any impact, the time dilation doesn't have any impact on how fast the Earth appears to be moving in a straight line. But it does have an impact on the rate at which it rotates. So we have the two different types of motion which are affected differently by special relativity, and should also be a clue to how space-time is supposed to work. Now there is a bit of a problem here, because if you imagine time dilation as a difference between the rate in which time flows for one observer relative to another, or in one frame relative to another, you can think of it as playing a video. So if I were to slow a video down, then everything that's rotating in that video and everything that's moving in a straight line in that video would slow down. So rotation would drop by say 50%, and motion in a straight line would reduce by 50% as well. But that's not what happens. That's not what special relativity or the idea of space-time, Minkowski space-time, claims. If you interpret it correctly, then it's really just saying that it's rotational motion, or time is really conceived of as rotational motion, or as a sort of cyclical motion. Like, it could be rotation, or it could maybe be a vibration or something like that, but not inertial motion. And the reason being, inertial motion happens in three dimensions. It's tied to an inertial frame of reference, but rotational motion is not, because it's frame independent. It's scalar. It only has one dimension, right? The speed at which something rotates is one dimensional. It can only rotate faster or slower. It's not a vector pointed in a specific direction. in three-dimensional space. So that's a good way to think about space-time. And I think what comes out of this is that space-time is a relationship between time and space, or that's how it's discussed, that's how it's presented. But really it's not. It's actually, if you think about it, it's a relationship between two types of motion. Not space itself, but inertial motion in space, and not time itself, but rotational motion, or sinusoidal motion, or some other kind of cyclical motion, but not motion that's directed in three-dimensional space.